Good morning to all. In this presentation, I'm going to talk about quantized conductance that we have seen in quantum point contacts embedded in LoSTO nanowires. This work is done at University of Pittsburgh in Professor Jeremy Levy's lab. As shown in the cover picture, when we measured the conductance of a small constriction, which eventually acting as a quantum point contact, we have seen a quantized conductance to the integer values of E square over H with respect to the gate voltage. Over the years, LoSTO interface system attracted a lot of research interest due to its novel phenomena happening at interface, where it was first shown to exhibit a high mobility two-dimensional electron gas at the interface, and in subsequent years two-dimensional superconductivity at 300 millikelvin, and also shown to possess various magnetic phases at the interface. This interface has a sharp insulator to metal transition near 3 to 4 unit cells of LeO, and 3 unit cells of LeO STO sample can be made conducting by applying a gate using strontium titanate, and this also can be achieved by conducting AFM technique, where when a positive voltage is applied to a tip, and it has shown that interface can become conduct underneath. We have used this conducting AFM writing technique to write these quantum point contact devices. First, we fabricate interface connected gold electrodes and desired these device structures written by controlling the position and motion of the AFM tip. Using this technique, nanowires were made down to 10 nanometer wire width, and these low dimensional devices have shown anomalous mobility enhancement at room temperature to up to 100 value. And recently we have also made quantum cavity dot like devices as shown in the figure, where and it has shown a Coulomb-Lockert behavior, which is a characteristic of quantum dots. Well, when in these ultra low dimensional devices, how far these electrons transport without any scattering? To know that, then we need to investigate the ballistic nature of transport. The ballistic nature of transport is very important to realize further exotic phenomena such as quantum Hall effect and possible edge state modes in these LoSTO nanowire devices. Basically, ballistic transport has been seen in nanowires and quantum point contact devices, where all you need to have is a nanoconstructions in which the density of states are tunable and they possess one dimensions of bands. The signature for ballistic transport is the conductance quantization, where the conductance of a device varies in an integer number, and this number represents the number of modes passing through this nanoconstruction. So we made these nanoconstruction devices using CAFM lithography technique, and we investigated ballistic transport in these devices. So a figure shows our device schematic, where it contains a nanoconstruction that is acting as a quantum point contact, and this nanoconstruction made by first writing a conducting nanowire by applying a positive voltage to the tip, and it also contains two insulating barriers which are written by applying a small negative voltage, and these weakly insulating barriers somehow controls the conductivity in these nanoconstructions very well, and the barriers having a width of 5 nanometers of each. These devices were cooled down to millikelvin temperatures in dilution unit. schematic shows our device measurement geometry, which contains four connecting electrodes and a side gate to the nano construction. We monitored source drain current by varying the side gate to the nano construction. As we can see from the figure that for large negative side gate values, the device can be completely pinched off and made insulating. We further measured source drain bias spectroscopy of this nano construction, and the results are shown in the figure. At 0 Tesla magnetic field, with increasing the side gate voltages, the conductance gradually increases, and near the zero bias, which is marked by a dashed line, the conductance converges for various gate voltages. The line profile at zero bias is shown in below graph, where you can see that the conductance is getting plateaued with respect to the side gate values, and at 9 Tesla these plateaus are more obvious and shows a clear quantization of conductance with 1, 2, 3, 4, so on values. Further, this zero bias conductance is measured over a magnetic field range of 0 to 9 Tesla and is shown in the figure. From the figure, it appears that these quantized plateaus appears to split at a certain magnetic field and from a single subband. To visualize the data better, we extracted a transconductance by performing a derivative of conductance with respect to side gate, and is shown in the figure. As you can see from the figure, it is obvious that the conductance plateaus split from the one subband, as you can see that the first plateau is splitting from second plateau, and the third plateau is splitting from the fourth one, fundamental. It appears that 2, 4, 6 are fundamental. It clearly suggests the splitting of these quantized levels in magnetic field. We attribute this subband splitting to the Zeeman splitting, which can resolve the spin subbands. In absence of magnetic field in a first subband, the up and down spin levels are degenerate and gives rise to 2 E square over h and absence of 1 E square over h. Whereas in the magnetic field, these up and down spin levels in first subband split with respect to each other, and the splitting strength delta E depends on the magnitude of the magnetic field and G factor of the device, and these sublevels can be populated by increasing the side gate. That's what we have seen of 1, 2, 3, 4 E square over h values. And to extract G factor, we have done a transconductance data analysis in the magnetic field range of 9 Tesla to 5 Tesla, where at each Tesla we extract the delta E value, and this delta E value actually can be obtained from the joining point of two arms in the transconductance data, which actually corresponds to the spacing between first two subbands. And we plotted delta E with the magnetic field and the slope, which eventually gives the Z factor, which is about 0.5 in these devices. And the splitting of these subbands, at least for the first subband in our device, is 30 micro EV per Tesla. We further analyzed the finite bias spectroscopy on our devices, and near zero bias, as I said, we expect to see integer 1, 2 E square or h values at devices, whereas for finite bias, since the source and drain potentials are not at the same, and at certain point one would see a fractional number of quantized values because the source and drain uh, slips the number of modes in number. And in fact, in our devices at certain finite bias values, we do see the fractional quantized conductance numbers, which further confirms that these nanoconstruction devices possess a one-dimensional subband structure, and they do split in magnetic fields, suggesting that spin resolved transport at higher magnetic fields in these devices. From the temperature dependent zero bias conductance measurements at 9 Tesla, it appears that the conductance quantization can persist up to 700 millikelvin in these devices, and above it start to gradually smeared out, and this is possibly due to enhanced thermal scattering at elevated temperatures. And we made longer devices also to see how long these ballistic transport exists in these longer devices, and we could see that the conductance quantization in devices that of 600 nanometers in length, which suggests that these devices having a ballistic transport through longer distances, and which could be interesting for looking at some other exotic phenomena in these systems. To summarize my talk, we hope we convinced you that we successfully made quantum contact devices that are embedded in LAOST1 nanostructures, and further we demonstrated that the conductance quantization in these nanoscale devices even appears in the devices with 600 nanometer in length, and the observed integer conductance quantization at higher magnetic fields imply a spin resolved transport in these devices, and this could be, we believe this could be crucial to investigate further topological and edge states in these LAOST interfaces. Thank you very much.